Welcome back, everybody. Thank you so much for coming. I want to just mention one thing. Tomorrow afternoon, if you're still around and you want some tips on where to go hiking, there's lots of great places of all levels, so you can ask me. And I also highly recommend going to the downtown mall. It's a pedestrian area tonight. Hopefully it won't be raining. You can walk from here and it's a nice place to eat and listen to music and get drinks. So otherwise, we're excited to start the morning with Oleksandr Tsymbaliuk. And on a personal note, thank you so much for the math you've done. It really helped my career. And I'm excited to hear you talk about the Lyndon and the shuffle algebras.
Thank you very much for the introduction. Very great honor to be here. So today we'll speak about coupled algebras and the first major part, mostly combinatorial aspects, and hopefully in the last 5-10 minutes, I will speak about some ongoing projects with Andrei Negut. So all of this is joint. So I'll start from something very combinatorial. So, but probably before that, let me like even outline where we are going to. So first I will recall Lalonde-Ram by Justin. Then I will recall Leclerc result. Leclerc has many results, but those that are relevant to this subject. And then you'll see the reproduction of this. And also a proof of Enriquez conjecture. So hopefully in the last few minutes I will mention about few studies. So all of this is about the algebra, moreover about quantum groups, but we will start from something very basic, namely some combinatorics. So let X be a finite ordered alphabet. And with that, I can compare lexicographically any two finite length terms. So X plus will be all finite length terms. The lexicographical alphabet. And the first of the two definitions on the combinatorial side is the notion of a Lyndon word. So if you have a word, we call it Lyndon. If it's smaller than any of its right phrases. So if you can write your W as a concatenation of two words, this is the prefix and this is the suffix. We require the W is smaller in the lexicographical order than any of its right phrases. Alternative definition, you could also say that W is less than all cyclic permutations. And everything's going to be structured about those words. So, kind of the idea is that you build up any word out of Lyndon words, and every Lyndon word can be kind of constructed from a ladder by following a finite. So, precisely, I need to give you a couple of basic definitions. So, definition one is a co-standard factorization. And it goes as follows. So if I start from a Lyndon word, which is a single letter, there is nothing to do. But if I have a Lyndon word which is of length bigger than 1, then I pick the longest Lyndon prefix. And automatically a simple exercise to show that L1 will also be Lyndon. So that will kind of allow us to give the definition of a bracket, which is related to the algebras in an iterative procedure. If they wrote of length 1, there is nothing. And the other one is a standard factorization, which basically allows to factorize any word, that any word in X plus can be written uniquely as a concatenation of Lyndon words in non-increasing order. 1, 2, K only. Okay, so those are kind of two basic constructions about Hindenburg. So why they are important in the context of the algebra? So the first result on the subject is very old, from the middle of previous century. Lyndon and also Tsymbaliuk at the same time. We say that Lyndon words give you a basis for a 3D algebra. So if you look at the 3D algebra generated by alphabet X, then its space is parameterized, can be parameterized in terms of Lyndon. So how does the construction go? At the Lyndon node, I want to predict an element in the leader. And that is going to be quite simple following that procedure. So if you have a single word, a single letter word, then I look at the element called bracket of X and just that element in my leader. Now, if I have a Lyndon dot of length bigger than 1, I will look at this co-standard factorization and apply the previous procedure. L is any Lyndon, look at co-standard factorization. And assuming that we know already what the elements correspond to L1, L2, I'll look at the commutation. This kind of inductive procedure. And that way we get a basis of the field. So that's a good result, but most of the algebras people studied, they're not real. They're quotient in 3 algebra per some idea. And kind of on the combinatorial side, you want to ask, can we describe those Lyndon words which will give you a base in that quotient? And the answer to that was given in the wonderful short paper by Lalonde-Ram a few decades later. And that will, so kind of question that we'll address. You'll see how even how to get bases. Well, the algebra by some idea. Maybe before we go here, let me just give a quick example. If everyone on page, just the simplest case of an alphabet which is not trivial, just 2 letters. And let's say that I have 2 letters, 1 and 2, and 1 is less than 2. So let's look at the example of the word 1, 1, 2. So 1, 1, 2 is lexicographically smaller than 2 and 1, so it is Lyndon. But for example, the word 1, 2, 1, 1, 2 is but that prefix is smaller.
Sorry, I can't read what's under co-standard factorization. It says longest Lyndon property and
Longest Lyndon prefix. So you take a word and you start reading off from the right, and you look at the longest word you can get, which is still Lyndon. And then it will automatically apply that what stays in the short part suffix is also Lyndon. You need that property. So kind of
what's on the left?
on the left will also be Lyndon.
Also Lyndon.
They kind of want to build to go from L to smaller rows. Right? So in that relation from combinatorics to the algebra, we are kind of doing some iterative procedure. You have 1 letter, this is your generator. If you have a word 1, 1, 2, you would take bracket of 1 with 2 and then bracket with 1. Okay. So let me just go in that example. The corresponding element in the algebra will be of the following nature. So that's how you construct element in 3D. So now, let's recall the result of Lalonde-Ram. So basically, they give a combinatorial description of nice Lyndon nodes. And so they call those standards. So this is kernel from that paper. But before we give definition, I'll need to give some construction. So let's double repeat any dot I1, I3 in this X plus, and I'll look at the element of of the corresponding Lie algebra, so called bar, which is basically I'm taking the product of those elements in the universal modality. Okay. So I think of those methods as all given elements in the Lie algebra G, which is kind of arising as a quotient of Lie algebra. And this is the element of universal modality. So now the definition is that the word is called Lyndon. If the corresponding element is not in the limit, is not in the span of such objects or figures. So it's kind of, you look at all words, not necessarily Lyndon at the moment. For each of them, you hook out an element in universal modality, and you look at kind of dominant one, dominating one. Those for which this element cannot be written as a linear span of the figure. And the theorem is that Lyndon laws, which are also standard, will give you a way. This is very general example. If I supply that if you look at the set of all those brackets for L, center, and Lyndon, then it gives you a basis of the algebra. So here we kind of pointed out that when we defined Lyndon words, there was no Lie algebra, there was just alphabet and a choice of an order. But the Lie algebra is kind of intrinsic here. But that definition I really use the specific order. Right? So this is very general result, but for the rest of today, we are gonna be interested in more studies. Lie algebras, which are simple finite dimensional Lie algebras of affine here. So for the next 10-15 minutes, I'm going to recall what happened for the case when G is a simple Lie. But before we go to any questions, our ultimate goal is to relate the combinatorics to affine Lie. But we'll start from here. So let's quickly recall what Ivan said yesterday. So this is a simple Lie algebra. The corresponding data will be the set of the root system, positive and negative roots. I'll call the simple roots by alpha I. And we have, so let's say generators, I'll use parts at the moment. If without parts for quantum group, so let's say generators. Subject to a bunch of relations. But I'm not going to write all of them because I don't really need to. I will, all of my discussion are going to be related to more or less half of G. And for that reason, I'll look at the subalgebra and ask inside G, this subalgebra generated by only positive elements. And as such, I can just say that this is the algebra generated by one set of elements subject to theory. Many times. Commutator BCJ, and you get it. And this is the algebra for which I will be connecting to the combinatorial. So, kind of the primary question is what that result tells you in that result. In my case, I will be only studying n plus, and what the result tells you that you construct a base from blocks. So there are many bases, but given that everything is graded by the root layers, that gives you a natural projection. So I can grade the rods by counting how many times every letter appears, and I can grade the Lie algebra G is intrinsically graded by the root layer. And all root subspaces are one dimension. So because all root subspaces, this is two stop. G alpha are one dimensional. So root subspace is open to us. We get a budget. This is called Lalonde-Ram system. Between algorithm L, so is a projection from the set of all positive roots to the set of all tensors in U. Kind of one piece of the data that is not appearing here implicitly is the choice of the order. So on that alphabet I choose, I make a choice of the order. Alright, so we'll get back there in a moment when we call the result. Yes,
Is G finite?
at the moment, simple finite dimension. Simple finite dimension. But I'm applying it not to the whole simple algebra, but only to the point.
So back to the theorem for the Lalonde-Ram, is a basis for n plus, not G.
Say it again.
That's a basis of G or a basis
So
of
this is
n plus.
like I stated, it is true for any finite dimensional D algebra. It is very general result. But I'm applying it to the case when G is replaced by positive part of simple D.
Very far.
Confusion of notation.
Yeah, maybe just erase this n plus over the finite dimensional over the thing.
Then the inverse for n plus. Let's do the question. Well, so before I give a more kind of explicit construction of that bijection, I'll need to say something about quantum proof because ultimately that's the goal of today's talk. So let me quickly recall Ding-Khoroshkin quantum proof. So closely follow Feigin notation. So use like different notation, like different generators, EI, FI, and phi I plus minus. That's the same as in Ivan's object, but use KI. Quantum group of G. And again, as in the previous story, I'm looking not at the overall object, but only as a point. I will look at QQ and plus. And this is a algebra generated by EIs and subject to this quantum theory. That everything is a time. Okay. So here is a deformation of universal value into n plus. So this object, when Q goes to 1, it degenerates to universal value of n. Right? So as such, one can ask, what are nice results about quantum groups? They're kind of coming as quantizations of something for Lie algebra. And one of the first results is a big double thing. This is a construction of Q. And his construction is not elementary in the sense that he constructs the whole action of the braid group and he builds his root vectors by the action of the braid group generator. And that is not being basically for every reduced decomposition. For the longest element in the file group, you can use the construct braid group action and use it to give a PW basis. Basically, UQ and plus is written as the sum over gamma 1, 3, positive roots. So one dimensional subspace is everything defined over rational function full view. E gamma 1, E gamma 2. And I'll come back to that in a moment. So basically, his construction uses braid group, and we want in a moment to eliminate it. We want to give it more combinatorial down to earth. Right? But let's get to where let's rock like one way. And to get kind of to relate quantum group to combinatorics, one needs to follow a different procedure. Instead of viewing quantum group as in many books and papers by generators and regulations, we want some technicality-free approach. And that is given by embedding it into some vectors. This is a Q-shuffle algebra. And this was undertaken around the same time by various people. So by Green, Rosso, and Tsymbaliuk. And the idea is to embed, instead of saying that your UQ and plus is given by a bunch of generators subject to some non-pleasant relations, rather embedded. And to say where we embed, I'll first introduce the overall space. So as an underlying vector space F is just labeled by the finite length. So this is all finite length. But we saw in the first minute of today's. Looking at the vector space is the space, but the product is not just continuous. If I want to multiply two dots, and that's enough, because everything is like this. What I will do, I will shuffle the letters. So I have A letters here, I have L letters here. I will permute them, but preserving the order of I among themselves and preserving the order of J. And if there was no Q, that would be the usual shuffle algebra, but because I want some Q deformation, I need to plug in certain parts. So what I will be doing is that I need to look at all the decompositions of the set from 1 to 8 plus 7 to 2 subsets. The domain is A and L. And there will be due to some power that I will write in a moment. And what will stay here is the word S1 space plus L, where each letter is getting generated from either that list or that list. The word is S, each letter SC equal to I dot, is equal to A dot, or J dot is equal to some kind of permuting those letters, preserving the relative order inside each group separately. And what the power of Q is kind of counting how many pairs of letters from one list and the other list are changing the order. Lambda AB is the sum over all A bigger than B, where it is an element from that subset, A is an element from the subset of A as A, alpha, alpha A. So whatever the power of Q is kind of uniquely determined, because our ultimate goal is to embed my UQ and plus into the algebra. So the claim that you can uniquely find those terms such that the following property UQ and plus embeds into that subset. So there are no labels here, so I just embedded. And you can actually explicitly describe the image. So this is kind of combinatorial approach. The pairing is just on the root labels given by the conjecture. So this symmetrized conjecture. Alright. So now that we related this, we can finally take like that.
Yeah, the exponent of Q depends on the underlying root system, but the multiplicative product depends only on this symmetric.
I mean, over here, G is assumed to be simple, yes. The exponent is just coming from counting kind of inversions, but it is using the symmetrized Cartan matrix of the underlying loop system. Yes.
I don't see how this is better. The simple product looks horrible to compute.
I mean, it's better. It's better in the sense that you can write down some element in the image, And there are simple criteria to check whether it is in the image or not. And kind of use it. Kind of the ultimate goal is that in the original quantum group, you have generators, but if you have some non-commutative polynomial of degree 6, it's hard to treat it. And here our ultimate goal is to use combinatorial approach, take some element, and once you know that it lies in the image, you can say something. You don't need to find explicit formula for it in terms of generators. All right. So for Leclerc, this was important for cluster algebra approach for what coming from finite quantum groups. In our case, I'm getting to the final sample algebra where it will be important. Okay. All right. So Leclerc algebra. So his first result is the explicit formula for Lalonde-Ram project. Now, one is explicit. Physics in the sense that it is easily programmable formula for Lalonde-Ram. And what it says is that L of alpha, so L was projection from positive roots to standard key intervals, is maximum of all combinations of two such laws where you look at all possible ways to split alpha as the sum of two positive roots, number 1, number 2 of position roots, and you order so that the first law is less. This is kind of very computable, and for example, Lalonde-Ram's paper, they gave a list for very specific orders of for specific choice of orders on alphabet corresponding to each into the algebra, but Leclerc's work gives you the full list of Lyndon standard words for any order of them. And all other results that you can develop, they are related to kind of this heuristic repeatability. And to get there, I need to mention one more property about this. So over here, we had a repeatability equation of quantum positive group in terms of break group generator. And we want to eliminate break group X. So for this, I already important Leclerc, sorry, not Leclerc, even though it's not a property. So it's not a property. We say that if you take two generators from heuristic construction and you order them in the wrong order, you can change the order and everything correction is lying strictly in between. Make it precise for any root alpha less than that, I can reorder the alpha in the following way. Look at this two commutator, and where it lies in is a span of ordered monomials sandwiched in between. So gamma 1 is and for the reasons, the sum of degrees is alpha. Okay, so it's kind of saying that if you start from not only you have figured out the basis for all algebra, but you can look at any two roots, look at all roots in between, and that will generate a subalgebra as well. And people still don't quite understand when these coefficients are zero. Many times this is zero. But let me just give an illustration. This kind of Q commutator. So when Q is 1, it becomes token. So now, why is it important? It's important for the following fact. That in some cases, it may be that there is almost nothing where the sum can take place. And this is, for today, the notion of minimal time. Application if alpha and beta are minimal pair. And what that means is the following. So that means that alpha plus beta is a root. But there is no way to write it down as a sum of two other restrictions. Every root can be written that for every root I can find a minimal pair, which writes it as a sum of two roots, and there is no smaller pair in between. And what that property tells me that for that case, the only guy that will feature in the right hand side is this E alpha plus beta. So let us go to the Feynman property. Tell that E beta E alpha Q is a multiple, non-zero multiple of E alpha plus beta. And that is the step if you want to undertake. So instead you kind of eliminate the braid group X and you recover elements as iterated Q commutations. That's the simplest example. Okay, please. Leclerc example. So, second result of Leclerc in that context is the one. So, yeah, this is to Rosso. So, we call this by Jackson, and then to the third. And on the right hand side, I have lexicographical order. I can compare any two rows. So I can pull it back and look at the order I get here. And what it, so if I look at the full back, the order that I get the order on theta plus, and that order is not. In the sense that it comes from reduced decomposition of double unit. So the statement, the theorem is that it comes from a reduced decomposition of W naught, which means that in that case I can apply Euclid construction to hook out all good generators, but at the same time I can build them without braid group X just by that's the perspective. Right? And finally, the third result connects kind of by Jackson L to actually quantum.
It's saying that it comes from gives you a particular choice of reduced.
It gives a particular, yeah, so those reduced, so kind of those orders on data plus which come from reduced decomposition of W, they're very nice, they're called convex. And convex means that for any two roots, if the sum is the root, it's strictly in between. So this is kind of combinatorial. And the result is that whatever choice on the alphabet you choose, the lexicographical order on the right hand side will always give you such a nice order on the So the final result of that is that I can actually combine several pieces from already previous discussion all together. So the result of that is the point. So let's recall, I probably can give this notation, the embedding of quantum group of quantum positive group into subset. So that was embedding to the subset. And let's look at the generator ELI. And ELI is constructed by this iterated Q commutator procedure. So every root gives you some element over here, and you look at the image. And the point that in the quantum world, you can recover back the word L5. So the claim is that it has the minimal leading term among all words in the image of that degree. And the leading term is exactly Li. And the leading term is precisely the word Li. So it kind of tells you that if you start from a root, L alpha was some standard Lyndon word, and you can read it back by first putting our generator in quantum group, mapping it to Shuffle algebra, and looking at the leading pieces there. All right, so let's do just one example electronic. For the type A, look at A and type is the one simple of that. 1, 2, 3, 10 minus 1, and the order will be the other. Okay. So what is going on? L, what is the dot corresponding to the root alpha I plus alpha j? Easy to guess, it's the dot where you put the letters effectively from I to j. And what is the corresponding generator? Alpha I plus alpha j is the iterated commutator. API EI plus 1, then you commute this EI plus 2, and so on. So this actually, this construction appears in one of the very first papers on quantum of Jimbo, when he treated type A. So he didn't have break progression, but he wrote everything as commutator in type A. Any questions? So that kind of computes simple linears. So for the rest, I'm going to discuss affine. So, I mean, one really wonders what happens for general Hertzsprung algebras, but already affine Hertzsprung algebras are not exactly well understood, I think. But it is a gift up. The rest. Affine Hertzsprung. Okay, so there are two perspectives on affine Hertzsprung. You can either start from extended thinking theorem, start from a set which is just bigger from I by an extended node 0 and hook out everything, or you can look at G hat, or you can think of G hat as the central extension of loop. And kind of this is one thing which distinguishes affine Hertzsprung algebras from all others. So what goes wrong with that? One can ask, can we generalize all the above to the present setup? Like, where exactly did we use that the Lie algebra was simple? And the answer is that unfortunately it doesn't generalize. Basically, the idea is that everything is the result of application of Lalonde-Ram projection to simple algebras was based on the fact that the root subspaces is pure one dimension, which is no longer true for phi. The dimension of G hat K data, imaginary root, is bigger than 1. So as you walk from simple roots up to data, everything works fine. But as long as you reach imaginary root, something breaks down. And not only it breaks down at the imaginary root, but it breaks down further because the way we construct the construction was kind of iterative. We reduce the root alpha to root gamma 1 and gamma 2. So that's kind of the biggest obstacle. So because of that, in the work with Andrei, rather follow that approach. This is our work with Andrei Negut. So let me quickly outline what's going on. So first of all, this is the overall algebra, but as in the classical case, I'm not looking at everything. I'm looking only at the positive part. In fact, I will be looking at loops of n plus. This is going to be n plus. So this Laurent polynomial thing is varies in n plus. The good thing of this is that it has one-dimensional root space. And they are parameterized by positive root and input. G alpha, which is it, I'll say plus alpha times t. All of them are one dimension. Now this is good. There is no difference. But the bad thing is that the construction of Lalonde-Ram does not apply on the nodes. And the reason for this is that the corresponding alphabet is infinite. Okay. Want to apply Lalonde-Ram and also Leclerc. but the alphabet is now parameterized by a simple root and an integer. The alphabet is parameterized by two pieces of data. I the finite set, I run through the finite set, and E runs through the integer. And that gives a little obstacle. It can be overcome, and the idea is kind of to use the algebra as a limit of finite dimensional issues. So we introduce standard Lyndon group doors for each finite dimensional issue, but then we need to show that they are compared. So let me first take what the final result looks. So on the root space, now that I replace n plus by the root into n plus, I will be getting not data plus, but pairs of elements from data plus and an integer. And on the right hand side, you can guess what you have. The same thing, the standard Lyndon rows defined appropriately in our alphabet. But to say this explicitly, I need to pinpoint very specific order on the alphabet. You don't know the answer for general order. So the order that we go with is the following. So the way we compare two letters is either the upper indices effect or is equal to E, but the index I is less than G. So it should be very specific order. And starting from it, we look at the lexicographical order on the finite length term. So what do we get is the following. First result is that we have a bijection from delta plus times, so this is the indexing set over set, and standard Lyndon group term. Moreover, if you look at the lexicographical order on the right hand side, and you look and you see which order is used on the left hand side, it is again convex. So the full bag of lexicographical order on the right hand side gives you convex order on left hand side. And again, let me write the conditions. So if alpha T and beta T are elements in beta plus T, such that alpha plus beta is also there, then convexity means that out of those three elements, the L is in between. So alpha plus beta TE plus E is less than maximum and bigger than minimum of those results. This kind of analog, good analog on the spot. And why do we care about that? Because we want to model Leclerc approach. We want to cook our root generators, not by having breakbook action, but rather by looking at the. And moreover, you can, looking at that picture, you can recover back Lalonde-Ram just by restricting to data plus times U. So if you look at finite set of pairs where the second coordinate is 0, you recover usual. Okay. So to state the next result, I'll need to introduce loop usual. So basically, the major result was to understand this bijet in terms of embedding of quantum group into chocolate. And I want the root version of this. So we had this F star, and now we want root version. This will be FL. So as an underlying vector space, it is here what it is. Vector space whose basis is a finite length dot. Vector space Q2. All those I want V1, V1, I but the product is more advanced. So if I want to multiply two such laws, then you get a sum, again, over all ways to split your set into two subsets of cardinality A and L. But you also have to allow now to change the exponents. Sum over all phi 1, phi k plus L integers is in sum zero. And basically, what you do, you write down some constant that I'm not. And the what you have here is similar to what it was in the final case. 1 plus 1 plus phi 1. And 2 plus phi 2, and so on. Sk plus L, k plus L, plus phi k plus L. So in the final case, we didn't have upper exponents, and those letters F you are coming from permuting I and J. So now F and G are coming in the same way. You permute in this I and J. You look at all shuffles, all permutations which preserve the order of I's among themselves and J's among themselves. But the coefficient again can be written down and is uniquely designed to have the following pattern. So this coefficient is cooked out to have the following proposition. That you have an embedding of UQ Ln plus into this faculty. Okay? So because of this and because of convexity property, you can define root generators here and you can look at the image. Like everything can be copy pasted more. But now, since I have only 3 minutes left, let me probably switch to the last part. This last mathematical part, which is the relation of all of these to Enriquez conjecture. So our original goal was completely different. We had a different type of algebra in mind, and we wanted to prove Enriquez conjecture, but in full generality there was not enough. So we had to go through this.
Its coefficients are integral.
Say it again?
Its coefficients are integral.
Yeah, they're integral. Yeah. Good question. So last part, trigonometric Feigin-Odesskii of algebras and Enriquez conjecture. So our main theory is actually a different type of algebra. Because all previous algebras we discussed, they were combinatorial in the sense that they had a basis coming from finite length blocks. But the algebra I'm going to introduce now is consists of symmetric factors, symmetric rational factors. Okay. Again, Feigin-Odesskii. But the construction goes in the present setup is close to me. Because the Feigin-Odesskii we consider big elements, and we need to apply this degenerated to trigonometry. So begin. So my overall algebra is going to be consisting of symmetric functions in as many variables as you like, but they are symmetric functions, where I range the two indices of my Ding-Khoroshkin diagram, and AI are non-negative. So look at all symmetric rational functions with poles and indices. So poles, I allow poles only at diagonal. Dij equal to djl, when I will equal to j. And the real conditions are as follows. So if we anything at certain potentialization, if I map di1 to w, di2 to w, qi negative 2, di1 minus aij to w, qi to aij, and dj1 to w, qi to aij. So the number of elements is the same as the length of two-sided relation. And this is kind of the idea to mimic what's going on combinatorically, mimic combinatorically quantum behavior. So this is my space. What is the algebra structure? The algebra structure is the following. You have some element of degree K and some element of degree L. Then the result is going to be of degree K plus L. And you separate your variables into two groups. I, R less than KI, G as the other group, and you add some rational factors. So those factors are going to be VI minus QI minus DJ e to the minus AJ divided by AJL and A minus GJL, where K is less than KI and L is bigger or equal than LJ. So you add a product of a bunch of rational terms as a game. This whatever you add here is uniquely defined to embed to embed UQ and plus into that. So a priori you could put many different factors, but if you want embedding, this is you need to discuss. And so final result is that this embedding is actually an algebraic term. We finish with this and kind of mention how is it related to the picture. Then, mention if I call this map option, it is algebraic term. Is always algebraic term for any simple geometry. Any simple finite-dimensional algebra G, and probably just in the last -2 remarks, how we prove it is exactly by relating this to the period. Okay, so the picture that needs to be drawn here that you have this embedding into A plus, and then we construct further embedding of A plus into this formal faculty, loop formal faculty. That map is what we had before, phi L. This is excellent. And kind of the point is that you have a bunch of embeddings. To show that this is surgeon, we need somehow to estimate dimension of the left-hand side versus dimension of the right-hand side. And it's hard to do for rational functions on themselves, but embedding into something combinatorial gives you. So both dimensions are coming from the same number of counting standard Lyndon loop. So I'm sorry, I'm out of time, but this is it.
Do we have any more questions?
Was this Enriquez conjecture?
Again,
What was Enriquez conjecture that this is the right?
conjecture that is always I don't. And it was proved in different, like, first it was proved by Andrei Negut, much other case 10 years ago. Then it proved it for some other types, but everything was kind of case by case.
For the finite type, the closed instructions closely relate to the dual canonical case. Actually, that also generalizes to the tuple. In this assigned case, you have some integral form. I want to what extent this question.
Exactly, and this is the last part that I didn't get. So to describe those integral forms, we don't know yet how to approach it that way. So that's the approach, but we rather want to classify them in terms of some descriptions for the rational function.
But of course, asking for canonical basis on this AOU class is unconventional already. But there was some work of Schieffelmann students or something, from certain algebra things seem to indicate the possibility, but they never continue. But at least if you do the intersection with the usual class part of Kazmuti, that part whether you have a good canonical basis.
No, I mean, from the perspective of just isomorphism of algebras, the natural question is classify what Ivan was speaking about the elliptic form or the continuous form in front of couple elements. So Leclerc did that for QQN plus, more or less. So in the case of QQN plus, you know how to do it in some cases, but in terms of this algebra A plus. Given an element over there, decide whether it is in the integral form or not. But we don't know the answer. And this is important for the application to geometric representation. We want to hook out elements in variant case A, not like a life, honestly.
Other questions? I have kind of a far-fetched question. I was just wondering, because from my perspective, I sort of think of the shuffle algebra and its connection to like the McDonald eigenoperators and stuff. So does your loop Lyndon word machinery have applications there? Have you thought about anything like that?
Not on the top of my mind. No. I thought about it, but it wasn't.
Yeah, okay, interesting.
But what you know is more about toroid.
Yeah, yeah. All right, oh, sorry, one more question?
I seem to remember there was a paper regarding like to construct that positive half of UQ, so UQN as like factorizable perverse sheaves on some type of like symmetric space, with like some type of shuffle algebra connection. Does this kind of
I mean, yeah, well, shuffle algebra construction comes indeed from convolution. That's very well explained in several ways. And also Friedman's complex. Like this computation just means on the level of fixed point basis how you can walk.
so the same type of shuffle?
Yes, yes, it has very nice geometric interpretation.
Okay, let's thank our speaker again.
And take a quick bathroom break.
Yeah.